functions actually. So, you can look at a logarithm of multiplicative functions which do not vanish. So, then that will give you an additive function. So, for example, this divisor function tau of n. So, this is the number of divisors. Number of divisors of n, then log of tau n is additive. So, this is multiplicative and then you get an additive function. So, this is multiplicative. And this is additive. This is additive. Yeah, so, one of our primary interest is going to be this this function which counts the number of distinct prime factors. So, while studying this arithmetical functions, we look at the mean. So, the average, let me start by looking at that, but just before that we define a notation because I would be using that. So, this is just a notation which I am going to use. So, write an integer in prime factors. So, this is over prime, a product over prime. So, p to the beta pm. So, let us have this notation where the product runs over distinct primes. So, beta p m is the power of that particular prime dividing m. So, this is a finite product because this is just going to be 0 except for finitely many p. So, that is going to be the notation, and one more notation is delta p of m. This is okay, let me just define. So, this is defined as 1 if beta p of m is greater than equal to 1 and it is 0 if beta p of m is equal to 0. So, in other words, this is simply an indicator function of divisibility. So, if p divides m, then you get 1, or if p does not divide m, then you get 0. So, this is just says that p divides m. If it divides m, then beta p m is at least 1, and this is just the case where p does not divide m. Yeah. So, now how do I write a additive function? So, if f is additive, so if f is additive, then f of m is going to be a sum over primes f of p to the beta beta p m. P to the beta p m. That is what you would get. And if it is completely additive, you would get something more. Completely additive, then f m is summation over prime delta p m f p, right. This is what you are going to get, because all these things are just going to be equal to f p. So, f of p to the beta is going to be f p. So, you have Fp at the point at the primes which divide M. So, both are finite sums obviously, because M has finitely many prime factors. So, yeah. Now, let us look at the mean. So, we would mostly concentrate on completely additive function. So, let us start with a completely additive function. Okay, I will keep this notation, maybe I just write here. So, if completely additive, so let us start with a completely additive function. Most of the time we will be concentrating on a completely additive function, and let us look at the mean, or you can call it average. So, it is the sum of summation m less than equal to n f of n then divided by 1 over n. So, we are summing from 1 to n of these values of this function, and then divided by the number of integers you are summing over, which is n. So, this is equal to now we have this expression for completely additive function. So, let us use that. So, I have a sum over prime delta p m f p. So, both are finite sums, so I can interchange. So, sum over prime f p then I have this delta p m. Now, what is this delta p m? The sum over delta p m, this is nothing but the number of integers up to n divisible by p. So, sum over p if p yeah. So, then this is m less than equal to n such that p divides m 1. So, for at all these integers m less than equal to n, if p divides m you count 1. So, that is exactly the function delta p m. So, you have this, and how much is that? Yeah. So, by the way, we can here as well restrict, because we are just going up to n. So, there cannot be any prime involved which is larger than n. So, we can as well put this to be less than equal to n, because as long as I keep delta p, it is fine. When I remove delta p, I should put something. So, this is less than equal to, let us make it like this. So, p less than equal to n f p, and this quantity is the integral part of n over p. So, which is roughly like n by p, and therefore, this sum is, so you have an n by p here. So, n cancels, and what you get is summation p less than equal to n f p by p. It is not exactly equal to, but roughly the same. So, that is the mean. That is the mean of a completely additive function. Okay. this is better. Okay. Now we just try to make a probabilistic model of this whole thing, of this additive function. So, especially this completely additive function. So, let me start by let me start by modeling this this delta p. So, delta p's are indicator function of divisibility by this prime. So, if p divides m, then you get 1, otherwise you get 0. So, it is a 0 1 valued function, then what should be the how do we attach the model? So, let us look at this thing, that what is the probability of divisibility by so by p of integers less than equal to n. So, what do what I mean is that for an integer less than equal to n, what is the probability that it is going to be divisible by p. So, if we just use our empirical definition of probability, then it is the number of favorable event by the all events. So, number of multiples of p number of multiples of p less than n by n. N is all the integers. So, number of multiple, so that is going to be again n by p So, this is going to be n by p, the integral part. So, that is the largest integer less than n by p divided by n. So, that is again roughly 1 over p. So, 1 over p should be the probability that this delta p is 1. So, delta p should be 1 with a probability 1 over p, and delta p should be 0 with a probability 1 minus 1 over p. So, we model, so we do not, so let's write down a model. We are not going to use the rough model, but we write down a model. So, let's consider this. Oh, this I have already used this notation. Let's say S. Yeah. So, these are integers up to n. So, integers up to n. So, that is our probability space, and probability is the uniform probability. So, every integer has probability 1 over n. So, uniformly, so everything is everything has the same probability of appearance. So, they have the same probability. So, p of, okay, we can also put this n here because the space depends on n, and maybe also p n. So, the probability of a number is 1 over p, sorry, 1 over n, 1 over n, 1 over n. And now define a random variable, say dp. So, define, this is random variable dp for each for primes. So, p is always prime, let us write just prime for primes less than equal to n, and dp is the model for this. So, we define it in the same way. So, dp probability of dp taking value 1 is 1 over p, and probability. So, this is our Pn probability. So, we are working on this space. One minus 1 over p. So, it is a Bernoulli variable taking these two values. So, yeah. So, this was the idea, but that is the model. So, I will keep the real world and probabilistic world separate as long as possible. Yeah. So, that is the model. And yeah. So, what is the use of such a model? So, if f is an additive function or f is any function C, then f restricted to this Sn is also a random variable, because any function is a random variable. Your sigma algebra is just the power set. Yeah. So, it is just the power set. So, any function is measurable, any function is random variable. So, in particular this any arithmetic function restricted to this Sn is a random variable on this space. So, okay, so then if it is a random variable, then what is the expectation? So, I will keep this E notation for expectation. Yeah. So, the expectation is obviously equal to the mean as we understand, because every integer has the probability 1 over n. So, it is simply 1 over n and then this sum. So, the value of the variable and the probability. So, this is exactly the mean. Exactly the mean in our this world. And yeah, so let's calculate this for additive. Okay, so additive functions we are going to model, because now additive function is not in defined that way. So, we would model completely additive function on this. So, how we model is this. Let me use the same notation so that I stick to my notes. Yeah. Yeah, so additive function, so completely additive function we have this, and now the model. So, actually I can leave this, that would be better. Yeah. Yeah. So, the model I would just call it gamma zeta p, zeta m, sorry, zeta m for m less than equal to n. This is, so just the same thing, summation p less than equal to p less than equal to m, in fact, if p dp. So, zeta p is a random variable. So, it is a random variable, it is a linear combination of this random variable dp, which we already defined. So, it is again a random variable. Yeah. So, what is the expectation of this? So, if you just calculate the expectation, then it is going to be, let me just write it, p less than equal to m. Yeah, because expectation is linear. Okay, let me mention that as well. Yeah. So, expectation is linear. So, you have this sum. So, p less than equal to m if p, then expectation of dp. So, expectation of dp takes value 0 and 1. So, value taken 1 with probability 1 over p. So, expectation is just 1 over p. So, this expectation is just 1 over p. So, what you have is p less than equal to m if p by p. And so, therefore, if I take zeta n, then it is going to be exactly the mean, exactly this quantity, which is almost the mean. So, then p is up to n if p by p. So, this is almost the mean. Now, the question is what is the variance? So, to calculate the variance easily, we need independence of these random variables. Then obviously calculating variance will be very easy. So, that is an assumption here. So, that is an assumption. So, we assume that dp's, so these are independent. So, these are a sequence of independent random variable, but they are not identically distributed, as you can see here. The distribution changes with p. So, they are not identically distributed, but we can assume them to be independent. And so, if they are independent, then you can calculate variance easily. Variance of this zeta n is the so that is the just from the definition. So, p less than equal to n. So, m is replaced by n. So, it is n if p square. So, for independent variable, variance is almost like linear, only that the constants come out as squared. So, this is f p square, f p is a constant. So, it is f p square into variance of dp. And the point is why we are saying that they are independent, because of this reason. So, we are modeling on things which are actually independent. So, because if you change prime, so divisibility by two distinct primes are independent events. You can see that empirically, because number of integers divisible by p times q is because that is going to be up to n is n by p into q. So, you can empirically see that these things are actually independent for distinct primes. So, that is why we are assuming this. So, we can easily calculate the variance now. And what is the variance of this dp? dp takes value 0 and 1. So, variance of dp can be very easily. So, this is expectation of dp minus dp square, my expectation of dp square into expectation of dp squared. So, expectation of dp square and expectation of dp is just the same, because it is a 0 1 valued random variable. So, this is 1 over p and this is 1 over p square. So, we have the variance. If p square into 1 over p 1 over p square. and this quantity is bounded by p less than equal to n f p squared by p. So, I am just ignoring the second factor. One important point to notice is that because it is 1 by p square, it is much smaller. So, we are not losing much by ignoring this, but nevertheless we get something bigger. Yeah. Expectation of expectation of dp, because it takes value 1 with probability 1 over p. So, into 1 into 1 over p plus 0 into this thing. So, that just goes away. So, just 1 by p survives. Okay. Actually, I am going very slow. Yeah, I can just, I need some time to come back to this. So, okay, let me erase this first. Yeah, so we will come back to the real world, but we need some more things from the probabilistic model. Okay. Yeah, so at this point let us give some names. So, this we are going to call it AN, or yeah. So, just remember this is going to be AN and this is going to be BN. So, just names for this, yeah, BN square, we are going to call it BN square. So, variance are usually written like that, sigma square, etc. So, I am just using BN square. So, this is AN and this is the expectation, and this is the this is not exactly the variance, but an upper bound for the variance, this BN square. Yeah, so now what we have, this is the expectation. So, let us look at this. So, we are using a Chebyshev's argument, a very standard thing we always do. So, variance of zeta n, yeah, I want to actually write the argument in one line. So, erase this as well. Okay, I am just trying to save some time. So, let us start with that. So, let this psi n be a function which is going to infinity as n goes to infinity. It can be a very slowly growing function, but nevertheless it goes to infinity, any function which goes to infinity. Then start with the variance of zeta n, which is expectation of zeta n minus the expectation of zeta n, which is a n. So, I am just replacing this by a n, zeta n, this is a n whole square. So, expectation of this quantity, and this we know that it is bounded by Bn square. Bn square is the notation for this sum. So, this is less than equal to Bn squared. Now, I am looking at a set, the probability of the set where this xi n xi n minus a n is bigger than epsilon psi n beta n, and then you have here epsilon square xi n square beta n square. So, this is just a Chebyshev's argument, right. This is, so if you have this full integral, here it is sum. So, it is a full integral, and then you have a, you get a lower bound by looking at the integral on a subset which is defined by this, and then this is the lower bound of the function on that particular subset, and the integral gives you the probability. So, just Chebyshev. Yeah, and I also have an epsilon here. So, epsilon, any epsilon. So, then what is the probability? Probability of xi n minus a n greater than epsilon psi n b n is less than equal to, so b n square cancels. So, I have 1 over epsilon square xi n square. So, this goes to 0, because for a fixed epsilon, if n goes to infinity, then xi n goes to infinity. So, this goes to 0. So, as n goes to infinity, as n goes to infinity. So, probability of, or in on yeah, so let me write that. So, probability of xi n minus a n by psi n b n greater than epsilon goes to infinity, goes to 0, goes to 0 as n goes to infinity. So, in other words, this quantity, this random variable converges to 0 in probability. That is the definition, right. So, this goes to 0 in probability. Now, what is the use of this? So, so now we go to the real world, where we were considering these additive functions. So, if I just translate this statement into that language, then what will happen? So, let me just translate that. I am sorry, I can't spend much time on doing that, but then let me just translate that. So, I am just simply translating this statement to the number world. So, this is the number of integers m up to n such that, or let us write such that if m minus a n by psi n beta n, this is greater than epsilon, this counting of this, into 1 over n, because 1 over n is the probability for everything. So, that is 1 over n comes here, and this goes to 0. N goes to infinity, and this is for a completely multiplicative function, because what we have modeled is a completely multiplicative function. So, this is a model for a completely multiplicative function. So, here what we get is completely multiplicative function, and these a n's are this just defined by this. This definition makes sense. This is not probabilistic. So, this is just the defined with numbers. So, that a n and b n are exactly the same quantities, and psi n is any function of n which goes to infinity as n goes to infinity. Okay. So, let me essentially just finish with the application. So, once we translate this probabilistic statement, which was very easy to prove, and to this number theoretic statement. So, obviously, this does not prove it. This does not prove it. This will require a proof, but this is what is expected from the probabilistic result. Yeah. So, if I now apply this to, so apply this to the omega, which is the arithmetic function counting number of distinct prime factors. So, if I apply it to this function, then what I can calculate, this is actually easy to calculate, that a n is going to be equal to b n square in this case, and which is going to be is exactly equal to sum over 1 by p less than n. So, reciprocals of primes up to n, and this is roughly log n. So, double log of n. And so, using here what we would get is the following statement. So, 1 over n, then cardinality of integers less than equal to n such that omega m minus log n half plus epsilon. Yeah. So, also I am taking psi n to be log n to the to the epsilon. Half comes from this. So, b n square is log n. So, log n to the half comes from b n. So, this is the epsilon. So, this goes to 0. Yeah. In fact, this statement can be. Oh yeah. Sorry. No, I should actually keep that. Yeah, better I just keep the same. Yeah, certainly. So, just keeping, so just keeping like this. So, this goes to 0 as n goes to infinity, and here you can actually replace this m by this n by m. So, that is a consequence, that is not too difficult to prove from here, that this is actually true, that m less than equal to n such that omega m minus log m log m is greater than log m. So, all n's are replaced by m, half plus epsilon, that goes to 0. In other words, for almost all integers m, omega m is almost like a double log of m, which is the Hardy-Ramanujan theorem. So, this is actually Hardy-Ramanujan theorem. Okay, so it's actually the time is up, and I really couldn't come to the Turan-Kubilius inequality, which was the title, but yeah, I can't help it. So yeah, so because if I yeah, so it actually comes if I want to really try to prove this, which I haven't. So okay, thank you.
If any questions, we can ask him after the talk. Okay, next talk we will proceed.
Yeah, sure.
Next
Oh, do I need it? I normally shout. Therefore, I thought I won't need it. Good. Essentially, additive combinatorics consisting of two types of problems. One, let us say for A and B are subset of integers, and then define A plus B, and A plus B is defined as elements n such that n can be written as A plus B. Okay. The point is that if a same n can be written as A plus B in two different ways, it is not counted twice. Okay. Therefore, it is counted only once. And that being the case, the question which you want to know is that if you have some information on A and some information on B, what can you say about the cardinality of A plus B? And conversely, if you have a cardinality of A plus B, what can you say about cardinality of A and cardinality of B? Therefore, there are two information, one is cardinality of A, cardinality of B, one is cardinality of A plus B. You see, cardinality of A plus B is not equal to cardinality of A to cardinality of B, because essentially because the multiplicity is not counted. Therefore, it may go down. Okay. And therefore, what is that you can say? This is one type of problem. The second type of problem is, suppose you take the natural numbers and break it to some finitely many classes. As Professor Adhikari has written in one of his books, we can probably look at a colorful thing, namely that this, for all the elements of C1 I color them red, and all these C2 I color them blue, and C3 I color them green, and C4 I color them yellow, which means that I have colored all the natural numbers. Disjoint union. Yeah, we only one color which we give. Okay, we have a disjoint union, and then what I want to know is that therefore, essentially C1, C2, C3, C4 are practically 1/4 of all the integers. Since they practically have 1/4 of all the integers, normally any property of the integers should be inherited by them, or at least should be inherited by at least one of them. Okay. Therefore, what are the properties that can be inherited from integers to at least one of them? Therefore, what are the properties which can be passed on from n to at least one Ci? These are the two type of problems which one will be interested. Okay. And since I do not have time to do either of them in well within 1 hour, I will confine to problem number 2. One of the main reason being, as far as the problem number 1 is concerned, that already enough experts there in this audience, including Professor Adhikari and Thangadurai, who are great experts in the type of these problems, given A and B, what about the A plus B, etc. And therefore, you may have some occasion to listen to them from there in this problem, and therefore, I will apply myself to this problem number 2. Okay. Therefore, the question is, what is the properties that I am thinking of? Therefore, let me took two properties. One, the equation x minus y plus z equal to 0 has a solution. The second, x minus 2y plus z equal to 0 has a solution. Of course, I mean, I am not going to write x minus 3y, x minus 4y, etc. These two will be sufficient for me. Okay. Now, let us look at the integers. In the integers, can you find out x, y, z such that x minus y plus z equal to 0? 3 integers x, y, z in integers, natural numbers, such that x minus y plus z equal to 0. Can you? You can, no? Yeah. Okay. For example, well, 1 to 1 to 1 is already a solution, and similarly for this. And now, the question which I am asking is whether I can do the same thing for C1. Therefore, I am now breaking this all the natural numbers into 4 classes, 4 colors, and would it be possible for me to have a solution in single color. Therefore, I want an x and a y and a z, all of them being red and such that x minus y plus z equal to 0. If you cannot do that, then find out an x, y and z, all of them blue such that x minus y plus z equal to 0. If you cannot do that, then try to get an x, y, z, all of them green such that x minus y plus z equal to 0. Okay? And the question which you are asking is whether it is always possible. Irrespective of how I am dividing it into finitely many colors, is it always possible that I will get a x, y, z such that x minus y plus z equal to 0. Okay? The answer to this question is yes, due to shoe. That if you take the integers and break them into colors of finitely many colors, then that already admits a solution of x minus y plus z equal to 0. Okay? But that is not obvious, that is not, I mean, because I can divide it in any way I want, and then I have to produce a solution. Any finitely many color, any color, any finite, 2 color, 3 color, 5 color, etc. 2 color it is easier, no? I mean, the more the number of colors is more difficult, because then you do not have many numbers. Less colors you can do that. I don't, no condition, no condition. But without any condition, even it is not so obvious. I mean, I do not put any condition at all. I just want an x, y, z all having the same color and no more condition, such that x minus y plus z equal to 0. Okay? And since I plan to talk about the B in little more detail, okay, let me dispose of the A part in 5 minutes and then come to the B part, which I will discuss later. Okay. Suppose, for example, the red has 50% of the elements and the blue has 20% of the elements and the green has 20% of the elements and the yellow has 10% of the elements. Then which is the color which you expect to give a solution? Sorry? Red. Red is the color. Is it always necessarily true that the red will give a solution every time, even though it has more elements? Okay? Is it really true that the red will have the solution all the times? Okay, let us try an example. Okay? I take the elements from 1 to 1000, there are 1000 elements, and in these 1000 elements, whichever integers ends either with 1, 3, 5, 7 or 9, I give a red color. Whichever number ends with 2 or 8, I give the blue color. Whichever number that ends with 4 or 6, I give the green color, and whichever ends with 0, I give the yellow color. Okay? Can the red give a solution for x minus y plus z equal to 0? No. Why not? X will be odd, then y will be odd, z will be odd, and there is no way x minus y plus z equal to 0. Okay? And is it possible that blue can give you a solution for x minus y plus z equal to 0? Okay. Therefore, essentially it comes from yellow. In some sense, what I am now trying to say is that there is a solution, but I cannot say that the bigger one gives you the solution. But that is all what I want to say about that, and now I want to say about this. Now let us look at x minus 2y plus z equal to 0. Yeah, this is what I want to talk about, that little more. Anyway, if a set does not have a solution for that, then this set is called sum free. That is, if you take 2 elements x and z, take their sum and that sum is not in the set, that is all what it means. If x minus y plus z is not equal to 0, then x plus z is not equal to y, which means that if you take two elements from the set and then take the sum, that sum is not in that set, and such a set is called a subset. Okay. And this set x minus 2y plus z equal to 0 has a solution. This set is called a 3 terms LAP, arithmetic progression. This is called 3 terms in arithmetic progression because x minus 2y plus z equal to 0 implies already that x, y, z are in arithmetic progression. That is the definition of being in an arithmetic progression. So, no, trivial solutions are never allowed. Yes. Okay, non-trivial solutions. Okay. In this particular case, it was proved by Van der Waalen. That if you take it and break it to finitely many colors, then at least one will have a solution to this equation for finitely many colors. Up to this, is it clear? Because now I am going to change the track. Okay? And from these observations, Erdős found that there is a difference between the two problems. In this particular problem, hopefully, the bigger box will give the solution. I mean, the smaller box also may give the solution, that is not the point. The point is that bigger box definitely gives you the solution. This is the conjecture of Erdős, which is not true for Schur's problem, as we said. The bigger box does not give the problem, actually the smaller box gives the problem solution, but already expected that this bigger box will give you the solution. In other words, if you have a positive density subset of integers, it should already have a solution. Good. In other words, if you have a set A such that A intersection 1, 2, 3 etcetera up to n divided by n and take lim sup as n goes to infinity, suppose this is positive, that is for the number of elements of A in 1 to n is at least constant times n. This again I do not need it for every n, but for an infinite sequence of n. For an infinite sequence of n, I want the number of elements of A in 1 to n bigger than constant times n. If that happens, already the equation x minus 2y plus z equal to 0 will have a solution. Okay. Therefore, what I am saying, therefore, this one I will have a positive density. This statement means positive density. Okay. Therefore, that is now the conjecture of Erdős. Therefore, the conjecture of Erdős says if n is k colored, no, coloring etcetera we have forgotten. If A contained in n has a positive density, then A has a 3-term arithmetic progression. When I say x minus 2y plus z equal to 0 or says that it has 3 terms in an arithmetic progression, both statements are equal. Because whenever x minus 2y plus z equal to 0, that would mean x, y, z are in an arithmetic progression. Correct? And anyway, he did not know how to prove it. And once you do not know how to prove it, then the obvious thing is to make the conjecture even stronger. I mean, even in weaker conjecture we cannot prove to make it little stronger. A has a k-term arithmetic progression for every k. Okay. Therefore, A has a 7-term arithmetic progression, A has 9-term arithmetic progression, and so on and so forth. Okay. That is the theorem which I want to talk about. Actually, I am not going to talk about that theorem, I am going to talk about a counter example to this theorem. Anyway, this theorem was proved for k equal to 3 by K. F. Roth, of course, who got the Fields Medal for a different work of his somewhere in 1953. And then of course, he summarily proved is the same result, and then summarily proved for k equal to 4, and then Roth proved for k equal to 4, etc., etc. And finally, in 1977, I think summarily proved it for all k, which is a proof in combinatorics, one of the formidable proofs. And then little later, I think in 1979, Furstenberg gave another proof again for all k, and 2001 Gowertz gave again another proof. And therefore, there are many proofs which would say that if you have a set A which has a positive density, A has a k-term arithmetic progression. Okay. After that, is it clear? Yeah. And now what is known? It is known that we do not even need a positive density. It is known that you do not even need a positive density, and if it in fact, if it so happens that the cardinality of A is bigger than n divided by a logarithm of n multiplied by log n power 4, then it will have a 3-terminal arithmetic progression. Now, okay, now I am only going to talk about k equal to 3. For general case, things are difficult. I am going to only talk about k equal to 3. And if cardinality of A is bigger than n over log n into log n power 4, then of course, it will have a 3-terminal arithmetic progression. Therefore, even if the set does not have a positive density, because if it has only n by log n into log n power 4 elements, obviously it has a 0 density. Okay, capital I have to define. Okay, what I mean is, I choose n first of all to be sufficiently large, and I choose the set A, not the natural numbers from 1 to n, for a sufficiently large n, and if I choose a set A contained in 1 to n, having a cardinality which is bigger than n over log n into log n power 4, then this set A will have 3 terms in an arithmetic progression. Okay. And now the question is, probably most of you know how many primes are there up to n. How many primes are there up to n around? I do not want an exact number because I myself do not know it, but what is the approximately how many primes are there up to n? Huh? Approximately n over log n. Okay? And therefore, what the number which I am having is a little more than that. If I can somehow reduce the log n power 4 and get 1 over n over log n, that would mean that the primes themselves have a 3-term arithmetic progression. Correct? This method will not work, okay, because I need now the cardinality to be n over log n by log n power 4. Therefore, it was a great surprising result due to Terence Stowe and Green, saying that the primes have k-term arithmetic progression. Therefore, if you take all the primes, you can find out a k-term arithmetic progression among the primes. Okay? And that you will not follow from this result, that needs a lot of other ideas. And then one can talk about the sets which are within the primes, which have a positive density among the primes, whether they will have a k-term arithmetic progressions, and there are very interesting results in those directions. Okay? Okay. Now that any mathematical structure should have at least a proof, probably I will give a proof of some statement, which probably may take 15 minutes, and therefore, I may not be able to do much, but let me give this proof little detailed, a proof due to Baron. The question is, therefore, how big, okay, therefore, I have I have 1 to n, and I have a subset of 1 to n, and I want a now having no 3 terms AP. Yes, yeah. This, no, A is a set whose coordinate is bigger than n over log n to log n 4. Oh, sorry, yeah. Okay. 3 terms of k equal to 3, sorry, I am only talking about k equal to 3. Okay. Oh, for general k, etc., such a result is not true. Therefore, that is why I am confining myself to k equal to 3. Therefore, I want a contained in 1 to n, which has no 3 terms arithmetic progression. How big a set A can get? Okay. Therefore, the question which I want to know is, how I want a set A contained in 1 to n having no 3 terms arithmetic progression, and I want to know how big the set is. Good. First of all, first obvious thing which you have to do is, if such a set exists, then you should have a pattern. You should know the pattern of the set. Then probably if you know the pattern of the set, then probably you can construct the set and then try to prove the various things. Correct? And when you are interested in a pattern of a set, how do you normally do it? Suppose you have a set in mind, okay? A set in mind, say with a property. I want a set with a property, and then I want that construct the set so that I can know the pattern. How will you normally proceed? The easiest thing is to go to the computer and ask it to produce you a set with that property. And once you do that, the computer will produce a set for you, and then you can analyze the pattern. And this method is normally called a greedy algorithm. Okay. Therefore, what does this method do? What does the method do is, the computer takes some number, let us say 17, and construct the numbers up to 17 in the set A. Having constructed up to 17, then it decides to know whether to put the 18 in the set or not to put the 18 in the set. And then it will just check, if you put the 18, whether it violates the condition you want. If it violates the condition, it will not put 18, then go to 19, but if it does not violate the condition, then it will put 18. And then it will take 19 and then check what happens if I put the 19 in the set. If you put the 19 in the set and the condition which you want is violated, it will not put 19, it will go to 20, but if the condition is not violated, it will put 19. As simple as that. Good. And this is what is called a greedy algorithm. Okay. And therefore, now let us say we go to the computer and ask it to produce it. And therefore, we will give the computer the first two numbers, 0 and 1. Then what will the computer do? It will check whether 2 puts it there. Can 2 go there? No, because 0, 1, 2 then will be an arithmetic progression. I do not want a 3-term arithmetic progression there. Therefore, 2 cannot be there. What about 3? 3 can be there, good. Let us put the 3. What about 4? Can we put 4? No, why not? 1 plus 3 equal to 4, no, we want 3 terms in a conversion. We can put 4. What about 5? No. Yeah, 6. It won't, no? Okay, I will leave it as an exercise. I will tell you a few more terms. I will leave it as an exercise to go to your computer and check this is precisely what the computer produces. That is the sequence which your computer will produce. Okay. Then first of all, I should know what is the sequence at all. Okay. Only then I will be able to see what is the pattern and then see whether I can construct something. Okay. You know, you can write the numbers in binary, no? That is what your computer does. You can also write numbers in decimal, which is what you do day and night. Okay. Suppose I decide to write the numbers which the computer has produced in the basis 3. Okay. You know, every number can be written in the base 3, no? Okay, let us try to write it in the base 3. Therefore, the first number is 0, second number is 1, then what is 1 1, then no, what do you get? 1 0, 1 0, 1 1, then 9 is what in base 3? 1 0 0, 1 0 1, 1 1 0, 1 1 1, so on and so forth. Okay? Therefore, the computer has produced numbers which avoid the digit 2 in the base 3. Okay. The computer has produced a set of numbers which avoids the digit 2 in the base 3. Is it okay? Probably we can try to do that. Suppose I take all the integers from 1 to n and write them in base 3 and whatever number which avoids 2 I will do and take the rest as a a. Hopefully, a may have 3 terms of arithmetic progression. Let us try that. Therefore, I have this number a, which I will call b1, b2, b3, etc. And what are the properties of this b? When this b I write in the base 3, all the digits are either 0 or 1 and there is no digit 2. Okay. Then can you say that if I take such numbers which have 0 and 1, the base 3 is 0 and 1 and avoids 3, then can we prove that such a number does not have 3-term arithmetic progression? The set does not have 3 terms arithmetic progression. Good. Let us try to prove that. Now, let us assume for example, a1, a2, etc. a are. Yeah, some of a may be 0 and therefore, I can assume every number is an r digit number by putting zeros, is not it? I can make every number to be every number less than 100 digit to be a 100 digit number by putting zeros in the beginning. Okay. Therefore, no problem at all. Therefore, let us say I can r digit number a1, a2, etc. a r, another r digit number b1, b2, br, and suppose it is equal to 2 times c1, c2, cr. Okay. Then I have to prove that a equal to b equal to c. That is the only solution. If I take a plus b is equal to 2c, then I have to prove that a equal to b equal to c, given this. But given something like that, these numbers are written in base 3, which means that this number by definition, the last number by definition is AR plus 3 times AR minus 1 plus 3 times 9 times AR minus 2 plus 27 times AR minus 3, etc., and the same thing for B and C. Good. How will you prove that? That it has only solution. First of all, let us make one observation. When I add this and this, and 2 is not one of the digits, and when I am in a base 3, then this addition is no carrier free, no carry over. Good. Because if you have a base 3 and if you have 2 numbers written in base, okay, let us say you have 2 numbers written in base 10 as usual, but all the digits are less or equal to 4. If you have 2 digits in base 10 and all digits are less than or equal to 4, and when you add, there will be no carryover. Correct? There cannot be a carryover, and that is exactly what is going on. We are writing the numbers in the base 3 and the digits are only 0 or 1, and if the numbers are written in base 3 and the digits are only 0 and 1, then there cannot be a carryover, which essentially means I can add these 2 numbers very easily and I know the result. Because there is no carryover. Therefore, when I add A1, A2, etc., AR and B1, B2, BR, the sum is A1 plus B1, A2 plus B2, etc., AR plus BR. Good. And now look at the right hand side. The C1 into CR I am multiplying by 2, but there is no digit 2, which means there is no carryover. Good. If there is no 2 in the digits, there is no carryover, which means I can even multiply the number C1 into CR by 2, and that number will happen to be therefore 2C1, 2C2, 2C2. Therefore, in base 3 a number has 2 representations. One representation is A1 plus B1, A2 plus B2, etc., AR plus BR. Another representation is 2C1, 2C2, 2CR. Then obviously, A1 plus B1 has to be 2C1, A2 plus B2 has to be 2C2, etc. But again, now look at A1 is either 0 or 1, B1 is again 0 or 1, C1 is also 0 or 1. And if A1 is 0 or 1, B1 is 0 or 1, C1 is 0 or 1, and A plus B1 equal to 2C1, that means A1 equal to B1 equal to C1. Can be 1. I did not say they are 0. I said A1 equal to B1 equal to C1. That is all what I need. Okay? That means the original numbers A plus B equal to A equal to B equal to C. Good. Therefore, the computer has given really a good set, which has no 3 terms in an arithmetic progression. This set which the computer has produced by the greedy algorithm is a set in which no 3 terms are in an arithmetic progression. Good. But unfortunately, this is not a big set. Okay. Therefore, we say why should it not be a big set? I leave it as an exercise that every digit has theoretically 3 possibilities, 3 power r, because this number will be something like a 3 power r of the same order, because an r digit number in base 3 will be of the order 3 power r, but every digit has only 2 possibilities. Therefore, this will produce only 2 power r elements. Therefore, your set A will have only 2 power r elements in 1 to 3 power r. Therefore, this set has, therefore, you have produced a set A in 1 to 3 power r, which has around 2 power r elements. correct. In other words, I have produced a set A in 1 to x which has around x power log 2 by log 3 elements. Correct. If 3 power r is x, the 2 power r is x power log 2 by log 3. I am not interested in that. I want a set which is x power 1 minus epsilon at least. Yeah, okay. A set A from 1 to x which is something like an x power 1 minus epsilon. Therefore, I am not interested in x power log 2 by log 3. Okay. And now comes a improvement which is slightly difficult, and therefore, let me explain. An improvement due to a guy by name Baran. Oh, 15 minutes, okay, I should be able to do something at least. Okay. His idea was, why am I looking at the 3? I can look at any other bigger number and try the same thing, and therefore, that is all what I am going to do. I am going to write probably in the base 11. Okay. And now I am going to take the set A which has in base 11 it has digits only 0, 1, 2, 3, 4, 5. Okay. In the base 11 if it has 0, 1, 2, 3, 4, 5, I go back to this argument. If there are 3 terms in an arithmetic progression, then A1 A2 AR plus B1 B2 BR equal to C1 C2 CR. And therefore, there will be no carryover because I am in base 11 and my digits are only 0 to 5, and therefore, this that would be A1 plus B1, A2 plus B2 etcetera, and this will be 2 C1 C2 etcetera, and this will be A plus of B1 equal to 2 C1, A2 plus B2 equal to 2 C2 etcetera. Up to that it is okay. And now, if A, B, C are between 0 and 5, I cannot conclude A1 equal to B1 equal to C1 from this. In the 3 case it was easy, okay. In the 11 case it is not easy, because in fact if A1 plus B1 equal to 2 C1, it does not mean A1 has to be equal to B1 has to be equal to C1. Good. You need something more, some more idea to somehow deduce A1 equal to B1 equal to C1. Okay. What is this idea? Okay, now let us look at this again. Now, what do I do is associate with this A, this number A, which is A1 A2 AR, okay. This is an integer written in base 11, correct. This integer A1 A2 etcetera is written in base 11 . Written in base 11, I am going to associate a vector A1, A2 etcetera AR in R power R. Okay. I take the digits and then put them as a coordinates. Good. Take them as the digits and put them as the coordinates. And then what this says, that A1 plus B1 equal to 2 C1, A2 plus B2 equal to 2 C2 etcetera. I claim this says that this vectors, the vector B bar, no, the vector C bar is a midpoint of A bar and B bar. Is it clear? Because the vector C bar is a midpoint of A bar and B bar is precisely the statement that A1 plus B1 equal to 2 C1, A2 plus B2 equal to 2 C2, A3 plus B3 equal to 2 C3 etcetera. Okay. Therefore, this is midpoint. Yeah, exactly. Midpoint is the line joining A bar and B bar. Okay. And now, what I did from this, I want to say, okay, I am not going to take all the A in the set which have digits only 0 to 5, but only those A's which lie on a certain surface, such that if there are two elements on the surface, the midpoint is not in the surface. What is the surface? You can easily think of that if you have 2 points, 2 distinct points on the surface, then you do not have the midpoint on the surface. Sphere. Okay, I have in 2 dimensions circle. Good. Therefore, that is exactly what I am going to do. Therefore, the idea, I will give you the idea first, and therefore, I take 1 to n. I take first of all A1. A1 is those elements which in the base 11 have digits only 0 to 5. Okay. And then out of this A1, I am going to take a subset A, which is a subset of A1, which was those elements of A1 which all lie in the same circle. All lie in the same circle. Therefore, I take a circle and I only look at this circle. Okay, say I am now confusing, and therefore, you should be careful, because on the one hand when I say A, I mean the number in integer written in base 11, and on the other hand when I say A, I mean after this identification to view it as an element of R power R. Okay. I do the identification. Therefore, on the one hand when I say A, it essentially means that I write in the base 11, and the other hand I say that it is an element of R power R. Therefore, in that sense, as an element of R power R, I want that all of them should lie in the same. Okay. Yeah, but how from this I want to deduce somehow that A1 equal to B1 equal to C1. Okay. Good. Therefore, since I have 10 minutes, therefore, let me complete the proof now. Okay. Just let me complete the proof, and I will leave most of the things as an exercise for you. Fix a D and an R, and I am going to look at the elements between 1 and 2D plus 1 power R, and going to write these elements in the base 2D plus 1. I am going to write in the base 2D plus 1, and there I am going to allow only those elements whose digits are 0, 1, 2, 3, etc. up to D. Once I assume that the digits are only 0, 1, 2, 3 up to D, then essentially it will be, we can ensure that there is no carryover, and the number of such elements is essentially D power R. Good. And corresponding to each A here, I can compute the A bar. Good. And therefore, the distance of A bar square is equal to A1 square plus etcetera AR square, and each A is less than D, and therefore, this is R times D square. Therefore, the distance square for all these points is at most R times D square. Therefore, by pigeonhole principle, I can find out another A1 which is contained in A, containing more than D power R over R D square elements, because that is the only possible distances from. The number of possible distances of these points from the origin is at most R times D square, and therefore, there is by pigeonhole principle there is at least one R which will contain most of the points, and in fact, that R will contain essentially more than d power r by r d square points, and that A1 I take. And then once all these points are on the circle of radius r, okay, and since the digits are between 0 and d, and therefore, I get up to this level, and now the fact that they are all in the circle of radius r means that A1 plus B1 plus equal to 2 C1 will already imply A1 equal to B1 equal to C1, because this circle cannot have 2 points, 2 distinct points and the middle point also, and therefore, this set is sum free. And now, I leave it to you for to choose the D and the R appropriately in such a way that this number will be bigger than or equal to the length of the interval power 1 minus epsilon, and that is possible by choosing the R appropriately. And since I do not have time for that, I will stop there.
Any question, please?
Yeah. Yeah, we want a very large sum free set, large sum free set. I mean, this is not the best that is known, but on the other hand, all the best that is known are all based upon the same idea. There is a positive density. As I was telling, I do not even need a positive density. If the set has more than n over log n times log n power 4 elements, already it will have a 3-term AP. There are results, yes, again essentially very weak, but essentially the same idea. I mean, there has been no new idea as such in this problem. Good, thanks.